Lab tutorial, and in this video we are going to look at whether mathematics is decidable or it is not decidable. So the fundamental concepts of mathematics that were disturbing the mathematical community when mathematics was developing. One of them was deciding whether mathematics is decidable or it is not decidable. Quite an irony there. So some of those questions. The first one was that is mathematics consistent or it is not consistent. Another one was that is mathematics complete or it is not complete. And the one which we are dealing with now is that is mathematics decidable or it is not decidable. So in this video we are going to look at whether mathematics is decidable or it is not decidable. So on the concept of whether mathematics is decidable or it is not decidable, we are going to first look at or consider the concept of set theory, and then thereby after that we will look at some few examples whereby it will be illustrated that on whether mathematics is decidable or it is not decidable. So before we proceed, I would like to say that this video was supported by Amazon Audible, more of Amazon Audible at the end of the video. So on set theory, so according to mathematics, a set is a collection of well-defined objects, and these objects, the set is included in these objects. So a set is a collection of well-defined objects with a set being included as one of the objects. So this improving whereby mathematics is decidable or it is not decidable using set theory, we'll first consider an example of a set which contains all the sets. So a set which contains all the sets, we will now try to decide whether this set actually contains all the sets. So I hope it's clear there. So what we are going to do is that we are going to consider if this set contains all the sets, it means that it contains all the sets including itself. So, and if it needs to contain all the sets including itself for it to become the sets of all the sets, it will cease to become the sets of all the sets because it is requiring itself to be part of it is requiring itself as one of the objects that are composed of it. So, and before the objects that are composed of it, we didn't know, since this set is one of the objects that is contains in itself, we cannot know whereby we cannot decide that it is complete, since we are trying to show that it is complete by including it as one of the objects that form it. I don't know if you are getting. So the main picture here is that if it contains all the sets, it does not contain all the sets. If it does not contain all the sets, then it contains all the sets. We are driven to the point of contradiction. So by being contradicted, we have actually proven that mathematics is undecidable. That's what we call proof by contradiction. So I know that might be a little confusing. Let us consider examples which are more relevant to us in our day-to-day life. The first example is that let us consider there is a student in class who can perform all the sums, all the questions that cannot be performed by other students. This might work well on all other students except the student himself or herself. But when we consider the student himself or herself not being able to perform a sum, what will be the condition of our statement? If you really think, you will realize that we will come into a point of contradiction, such that will be the statement will be like, if this student can do all the tasks that the other students cannot do, then he cannot do. And if this student cannot do all the tasks that all the other students cannot do, bearing in mind that all these students has this student who is performing this task to be included. So if he can't do all those sums, then he can't. If he can't, then he can. We are contradicting ourselves. So it further proves the point that mathematics is undecidable. Maybe another example. Let's say there's a barber in a certain village, and this barber can only shave those people who cannot shave themselves in that village, bearing in mind that this barber is included since the barber lives in the village. So it works well for all other people, but when we come and consider the barber himself or herself, then we are contradicted, because if the barber can shave himself or herself, then he can't, and if he can't, then he can. A point of contradiction. So on all those examples, we have proven that mathematics is undecidable. So this is contrary to our normal thinking, because we usually think that we are decidable, we have that capability to decide. So that is not true, because we have shown that mathematically speaking, we are undecidable. This is not just in mathematics, it also appears in all those other sciences. For example, in physics, the concept of undecidability is very prominent, especially in quantum mechanics. So also it brings into light that even our thinking, we are undecidable, since because mathematics is the basis of all computing, and actually our minds, we are computing. So it means that we are all undecidable. We cannot decide, since mathematics is undecidable. All the computation, there is a point in computation whereby we cannot decide. We are undecidable, and it's not because of lack of information, it's just the fundamental truth of nature. I think that's clear. That's the end of this video. So as I had said earlier, this video was supported by Amazon Audible. Amazon Audible is this collection of books, different types of books, both in the field of mathematics, sciences, engineering, even novels. And instead of reading them, you can have someone read out for you, and you will be listening to them in form of podcasts. So to sign up for Amazon Audible is very free. So you can sign up for free using the link on the video, or you can get the link down in the description. I want to thank Amazon for supporting this video, and I want to thank you for listening or for watching. Thank you.